Welcome to this presentation on forestry applications for the GIS analyst. Geospatial technology is an invaluable resource in order to understand, communicate, and make effective decisions about conditions on the ground. Geospatial technology helps foresters in the acquisition of the data that is necessary to further research and to manage and recover present and future conditions of global forests. GIS uses different levels of geographic and geospatial information, such as elevation, hydrology, or the location of roads and infrastructure, to create a multi-layered representation of a site. There are many different forestry applications depending on the nature of the land usage objective. For reconnaissance mapping, some objectives for national forest or environmental agencies include updating of forest cover information, depletion monitoring, measuring biophysical properties of forest stands, forest cover type discrimination, and agroforestry mapping. For the commercial forestry industry and resource management agencies, useful inventory and mapping applications include collecting harvest information, updating of inventory information for timber supply, broad forest type vegetation density and biomass measurements, clear-cut mapping, regeneration assessment, burn delineation, infrastructure mapping, operations support, forest inventory, biomass estimation, and species inventories. For environmental monitoring, conservation authorities are concerned with issues such as monitoring the quantity, health, and diversity of the Earth's forests. They look at things like deforestation, for example in the rainforest or in mangrove colonies, species inventory, watershed protection, such as riparian strips, coastal protection for mangrove forests, and forest health and vigor, as an example. International and domestic forestry applications can make use of remote sensing data for sustainable development, biodiversity, land title and tenure, and many of the previously mentioned environmental concerns. General forest cover information is valuable to developing countries with limited previous knowledge of their forestry resources. General cover type mapping, shoreline and watershed mapping, monitoring for protection, monitoring of cutting practices and regeneration, and forest fire burn mapping are global needs addressed by forestry agencies and companies employing remote sensing technology as part of their information solutions in foreign markets. Natural disasters also play a role in forest management in that they can wipe out huge areas of forests. Burns can destroy several thousand of hectares, landslides can displace trees down a slope, and the excessive flooding can damage trees. Volcanoes have the greatest potential for destroying forests in the shortest amount of time. The volcanic blasts from Mount St. Helens, for example, reached 320 kilometers per hour and leveled over 600 kilometers squared of forest. For many temperate forest application requirements, high accuracy for accurate information content, multispectral information, fine resolution, and data continuity are the most important things. There are requirements for large volumes of data and reliable observations for seasonal coverage. There's a need to balance spatial resolution with the required accuracy and costs of the data. Resolution capabilities of 10 meters to 30 meters are deemed adequate for forest cover mapping, for example, also for identifying and monitoring clear cuts, burn and fire mapping, collecting forest harvest information, and identifying general forest damage. Spatial coverage of 100 to 10,000 kilometers squared is more appropriate for district to state or provincial scale forest cover and clear-cut mapping, whereas 1 to 100 kilometers squared coverage is the most appropriate for any site-specific vegetation density and volume studies. Tropical forest managers are most concerned with having a reliable data source, capable of imaging during critical time periods and therefore unhindered by atmospheric conditions that often occur in those regions. A combination of classification and thematic change detection can give valuable information about a harvest area, including the amount of forest harvested over a longer term or year over year. We will examine both temporal situations in this example. The data used in this example includes Landsat TM and ETM Plus scenes from 3 different years, including 1999, 2005, and 2006. We will look at the changes over the longer term and the year-over-year changes in a harvest area just south of Lake Tahoe, California. The first step in the process of quantifying the harvest area in this tract of forest land is to perform a classification on all 3 datasets using ENVI's classification workflow. We will use the Landsat ETM Plus scene from August of 2005 in this example, but it will be performed on all 3 datasets. Landsat data is freely available through the Landsat archive. With some of the later scenes, there's a noticeable striping due to a failure of the scanline corrector, or SLC, in 2003 and later scenes. The datasets are still usable, but for visualization purposes, they need to be gap-filled and radiometrically corrected. In this case, we will use a tool from our public code contribution library available on the excelisviz.com website to perform the gap-filling process. All of the scenes were radiometrically corrected using ENVI's Landsat calibration tools. Once the data is pre-processed, it is really easy to perform the classification. The classification tool allows you to choose training classes and preview the results on the fly so that you can fine-tune the analysis with an appropriate level of training classes to be able to accurately get the information you're looking for. In this case, we want to look at newly harvested cut blocks, so we've created a separate class for regrown cut blocks, which appear light green in the true color RGB composite of this image from 2005. After initially processing the entire scene and performing a smoothing cleanup function, we want to export both an image representation of the classification as well as a vector output. The image allows you to visually see what's happening and can be used in a tool such as thematic change detection to get a good visual interpretation of the newer cut blocks year over year. The vector file can be imported into a tool like ArcGIS to perform a quantitative statistical analysis to determine the actual total area harvested year after year. So taking the vector file and loading it into ArcMap, you can then select by attributes to isolate only the clear-cut classes. You can then create a feature layer out of the selected clear-cut classes and use some spatial statistics to compute the area of the polygons for the clear-cuts. The final step is to use the summary stats tool in ArcMap to compute the sum of all of the polygons. So you can see in the August of 2005 scene, the total area is 18,121,700 meters squared, or roughly 4,478 acres of harvested area. The same process can be followed for the 1999 dataset, as you can see here, and the 2006 dataset, as you can see here. The total area for 2006 was 23,316,390 meters squared, or 5,761 acres, definitely up from 2005. The total area from the 1999 dataset was only 14,300,600 meters squared, or 3,533 acres. This gives us information about the change in the harvested area over the longer term. We could do an additional analysis to include the regrowth from earlier scenes for comparison purposes, and we could also do an analysis of the actual forested area that is intact. Landsat data can be really useful for these types of landscape level analyses, and using ENVI in conjunction with a tool like ArcMap can make it really simple for visualization and analysis of Landsat data for forestry professionals. On this last slide, we're showing a visual assessment of harvest levels from 1999, 2005, and 2006, respectively, in ENVI. It's very clear that you can see the differences in terms of the amount of harvest between 1999 and 2005, and again year over year between 2005 and 2006. This concludes the presentation. Thank you, and if you'd like more information, please contact us at info@excelisviz.com or visit our website at www.excelisviz.com, or you can also look at any of the social media sites listed here.